Buffers. A buffer is a solution that contains a weak acid or a weak base and its salt, which is its conjugate and resists sharp changes in pH. Buffers cannot be made up of strong acids like hydrochloric acid, hydrobromic acid, or sulfuric acid, or strong bases like lithium hydroxide, sodium hydroxide, and barium hydroxide, because they completely dissociate. Buffers solutions are resistant to pH change because of the presence of equilibrium between the weak acid and its conjugate base, or the weak base and its conjugate acid. The bicarbonate buffer system is an example. In a part of the bicarbonate buffer system, carbonic acid partially dissociates into a hydrogen proton and a bicarbonate and vice versa. The acidic species neutralize hydroxide ions and the basic species neutralize hydrogen protons. When a small amount of hydroxide ions are added to the buffer, the hydroxide reacts with the carbonic acid to produce bicarbonate and water. Similarly, when a small amount of hydrogen protons are added to the buffer, the bicarbonate is consumed to produce carbonic acid. In both instances, the bicarbonate to carbonic acid ratio remains fairly constant, so the pH does not significantly change. There are 3 ways to make a buffer. 1. Use a conjugate acid base pair with a pKa the same as the desired pH. 2. Use a conjugate acid base pair with a pKa close to desired pH and then add strong acid or strong base to get the exact pH required. 3. Use a weak acid or weak base and partially titrate that with a strong acid or strong base. By neutralizing a portion of the weak acid or base, a salt is formed that contains the conjugate of the weak acid or base. The Henderson-Hasselbalch equation can be used to find the pH of a buffer. Here, HA is the molar concentration of the undissociated weak acid. A is the molar concentration of the acid's conjugate base, and pKa is the negative log of Ka, where Ka is the acid dissociation constant. In the alternate equation, BH plus denotes the molar concentration of the conjugate acid of the corresponding base B, which is also measured in molarity, and pKb is negative log of Kb, where Kb is the dissociation constant of the base. If the pH equals the pKa, the log of the ratio of the acid-base conjugate pair will be 0, so the concentrations of the 2 species will be the same. In other words, when the pH equals the pKa, the acid will be half dissociated. If the pH is below the pKa, then the ratio will be less than 1. Contrary, if the pH is above the pKa, the ratio will be greater than 1. Diluting a buffer does not change its pH because the ratio of acid and base does not change. Buffering capacity is the amount of acid or base that can be neutralized by the buffer before significant pH change, and the buffering range is considered to be pH equals pKa plus or minus 1. Since some buffers change color over their buffering range, they can be used as indicators for titrations. An example is phenolphthalein. For both titrations shown, the buffering zone is before the equivalence point.